Okay, good morning to everyone. Okay, today we're going to present resonance RLC circuit, parallel circuit. Okay, and your presenters are Luqman Nur Hakim, Muhammad Zakwan, Nur Fitri, Ifan, and me, Sanjay. Okay, first presenter is Muhammad Zakwan, and I would like to pass to him.
Thank you, Sanjay. My name is Muhammad Zakwan. I will present about the theory resonant RLC parallel circuit. Okay, next slide, please. Okay, resonant. In term, resonance is very useful in communication system including radio, television and telephones, as well as machine control system. The circuit behavior is determined at a selected frequency for a specific purpose. This allows the circuit work effectively at optimum frequency or resonant frequency. Next slide. Okay, resonant have two type of circuit, that is series resonance and parallel resonance. Okay, I want to talk about more about parallel resonance. The resonance of parallel RLC circuit is a bit more involved than the series resonance. The resonant frequency can be defined in three different ways, which converge on the same expression as the series resonant frequency if the resistance of the circuit is small. The frequency at which omega L equal to 1 over omega C, the resonant frequency of the equivalent series RLC circuit. This is satisfactory if the resistance is small. The frequency at which the parallel impedance is a maximum. The frequency at which the current is in phase with the voltage unity power factor. Okay, last. At resonance, there will be a large circulating current between the inductor and the capacitor due to the energy of the oscillation. Then parallel circuit produce current resonance. This is the circuit for the parallel resonance. Okay. Okay, now I will pass to Luqman Nur Hakim. Thank you.
Thank you, Zakwan. My name is Luqman Nur Hakim Abdul Qadir, and I'm going to present on the calculation part of the resonance in RLC parallel circuit. Okay, so for the first one, I'm going to talk about the resonant frequency. Okay, so based on our circuit that is in the slide, we can see that we have to find, firstly, we have to find the inductive branch current, which is IL, and the formula is V equals to, V over square root of R square plus 2 pi F L square. Then we have to find the capacitive branch current, which is 2 pi FC. Our phase angle between IL and V is theta equals to inverse tangent 2 pi FL. Okay, from our graph at below, we can see that we can get the inductive reactance formula based on the graph, which is XL equals to Z sine theta. So we will work out on it, and we can get sine theta equals to XL over square root of R square plus 2 pi F L square. Okay, next we have to find the IC. Okay, from the graph below, we can see that the IC is equals to IL sine theta. So we know that IC is 2 pi F CV. So next we just have to put in all the formula inside it, and we can get 2 pi F CV equals to 2 pi FLV over L square plus 2 pi FL square. Okay, so our frequency resonance or resonance frequency is 1 over 2 pi square root of 1 over LC minus S square over L square. Okay, so when our value of R is much smaller than XL, we can get the FR equals to 1 over 2 pi square root of LC. Next, I'm going to talk about the quality factor. Okay, so for both series and parallel circuit, to get the Q factor, we can use the same formula, which is reactive power over average power. So we know that it is I square XL over I square R. Okay, we can just cut out the I square part, and we can just left with XL over R. We know that XL is omega L, so we just substitute it with omega L over R. So for my last slide, I'm going to talk about the dynamic impedance, which is ZR. So we know that first we have to find IC from our left side of graph. You can see that our IC is equals to I tangent theta. So we have to put the I as the title, which is I equals to IC over tangent theta. So we know that our ZR is equals to V over I. Okay, so we just substitute our I with V equals to IC tangent theta. So we just substitute everything with 1 over 2 pi FRC times with 2 pi FRL over by R. So we just cancel out the 2 pi FR part from both sides. So we can get the last formula, which is L over CR. That's all from me. Thank you. Now I'm going to pass my to my friend Nufitri. Thank you.
Okay, hi, Assalamualaikum. My name is Nur Fitri bin Muhammad, and I will present about parallel RLC circuit. Okay, this is the circuit, parallel RLC circuit, that we know that source is 5 volt and the frequency is 50 hertz, and the resistor is 0.2 ohm, inductance is 100 micro Henry, and then capacitor is 2 microfarad. Okay, this is the calculation of parallel circuit. So this is reactance, inductor, and capacitor. So XL is in reactance inductor, which is 2 pi FL, and then we key in the data is 2 pi times 50 times 100 micro, so equal to 0.031 ohm. So the XC is reactance capacitor. So the formula is 1 over 2 pi FC. And then the answer is 1591.55 ohm. So this F is frequency resonant. So it's, the formula is 1 over 2 pi square root 1 over LC minus R square over L square. So the answer is 11249.45 Hertz. And then the Z is total impedance. The formula is R plus J bracket XL minus XC. So the answer is 1591.52, and the angle is negative 90 degree. Okay, the FR is 1 over 2 pi square root LC. So the answer is 11253.95 Hertz. So this is the finding current. So IL equal to 1 over square root R square plus bracket 2 pi FL and close bracket square. So the answer is 4.94 ampere, and the IC is 2 pi FC times V. So the answer is 3.1142 milliampere. So I coil equal to V divided Z total, so equal to 3.14 ampere. Okay, that's all from me. So I will pass it to my friend Irfan Hakim.
Okay, thank you to Nufitri. Okay. Sorry, there's some technical problem. Okay, today I'm gonna present about Q factor and dynamic impedance. So first we must find dynamic impedance, which is the formula is ZR equal to L over CR, and then we substitute the value. So the answer is uh, 250 ohm. Then we find current. So the formula is V equal to ZR. So then we substitute the value, and then the answer is 0.02 ampere. Then we can find the Q factor, which is the formula is omega L over R, and the answer for the Q factor is 0.155. Okay, next. Okay, so for the conclusion of the graph, in the RLC circuit, the opposite to series circuit, so we can actually decrease supply current to something that very small in comparison to separate current, which is I coil and I capacitor, that withdrawing in the branches of the circuit and what we actually see. If we plot IS against F for parallel circuit, is something look more like this figure, as you can see it. Then we get this inversion in the graph. So what our resonant frequency, we're actually drawing the smallest current that we possibly can in our circuit. So I'm gonna pass to my friend Sanjay.
Thank you, Irfan. That was very enlightening. Okay, now I shall show you how to set up the RLC circuit, which can have a resonance in a resonance state. Okay, the first thing you're going to do is get your multimeter, get your source, your resistor, your inductor, and your capacitor. You can find it at the top left corner. And you just set it up as I shown over here. Since I've done it over here, so it's going to be time saving. So let's straight away look at the values. Okay, for the V supply is going to be 3 volts across this supply, and the current, which is the current across R and L. Since it's in a series state, it's going to be the same current. It's not going to be different. And the IS is going to be the same because it's in series with the source. Okay. Okay, let's go see the current values first. Okay. For the IR, it's going to be 24.6 and the IC is 3.1. Okay, if you're going to search for IR, okay, you just have to click over here at the red line. You just right click, select a trace, pick whichever trace you want, and then click OK. Select right click again, go to the nearest Ymax, and that's how you get your values over here. Okay, that concludes my presentation. That's all for today. Thank you very much, and I bid you farewell.